All right, in today's video we're going to be doing a key for the 1999 question on the AB test number 3. I've classified this as a type 1 and a type 5 question. It's type 1 because we're going to be talking about rates and accumulation, and then it's also type 5 because we're using a table to do calculus. So let's get started with part A. So we're given a table which shows the rate of flow of water through a pipe over a 24-hour period, broken down into 3-hour increments. And they want us to use the midpoint Riemann sum with 4 subdivisions of equal length to approximate 0 to 24 integral r of t. So we are going to be approximating r of t integrated on the boundary of 0 to 24 using the midpoint Riemann sum with 4 subintervals. So if we look at our delta t, b minus a over n, we see that our delta t is every 6 hours. And we want to use the midpoint Riemann sum for that, so the interval 0 to 6 is going to have a midpoint of r of 3 times our delta t. Our next midpoint from 6 to 12 will have a midpoint at 9 times our delta t. And then the interval from 12 to 18 has a midpoint at 15 times our delta t. And then finally our last interval of 18 to 24 has a midpoint at 21 times our delta t. If we evaluate all of this out, we're going to have 10.4 times 6 plus 11.2 times 6, 11.3 times 6, and finally 10.2 times 6. Now this is a numeric answer and would give you credit, but if we turn to a calculator, because it is a calculator active question, we can add this up fairly quickly and we get 258.6. And if we do a little bit of a unit analysis on this, r of t represents gallons per hour and delta t represents hours. So gallons per hour times hour would give us gallons. So the meaning of this, approximately 258.6 gallons of water flows out of the pipe in the 24-hour period. 24-hour period, t equals 0 to t equals 24. I'll talk about the grading when we get all the way done to part C. So let's go ahead and move on to part B. Is there a time in the interval 0 to 24 such that r prime of t equals 0? So we're asking a question about the existence of a point where the derivative equals 0. So we should turn to our existence theorems, and the existence theorems about the derivative equaling a specific value are going to be either the Rolle's theorem or the mean value theorem. And remember, Rolle's is just a special case of the mean value theorem. Rolle's is the case where the derivative equals 0. So we're using Rolle's theorem, but it can be justified just as well with the MVT. And Rolle's theorem says if 3 conditions are true, we can make the conclusion about an existence. So the 3 conditions are r of t is differentiable on 0 to 24, and that's given to us, so we know that's true. The second condition is r of t is continuous on the closed interval 0 to 24, and we know this is true because it's differentiable. that because r is differentiable. And finally, the last condition is that there are 2 points where the function is of the same height. And r of 0 equals 9.6 and r of 24 equals 9.6. So all three conditions are met. So there exists a value, we'll call it a value c in 0 to 24 such that r prime of c equals 0 by the Rolle's theorem. All right, moving on to part C. Part C, they say that the rate of flow of the water can be approximated by Q of t, and Q of t is given. So what they're saying is that these points here belong to the curve r of t, but r of t can be approximated by Q of t. In other words, if you did Q of 0, you would basically get 9.6. Q of 3, you would basically get 10.4. So that's a approximating function. And they say use Q of t to approximate the average rate of water flow during the 24 period. So they're asking for the average value of Q of t, since Q of t represents rate of flow. So the average value of Q of t. This is an average function value question. So we know the average function value can be written as 1 over b minus a to b, of the function that we are approximating the average value of, or actually calculating the average value of. So for us, we will have 1/24, 0 to 24 of Q of t. Now, since they identified Q of t, we could write in Q of t dt, or we could write it in the whole equation, but that's a little dangerous because you might get a copy error there. So now we need only evaluate this definite integral, which would take time doing by hand, but it is doable by hand. Fortunately for us, this is a calculator active question, so we can evaluate this by turning to our calculators. So let's do that. So first off, what we'll do is on the calculator, oftentimes if we are going to be using a function multiple times, it's worth putting it into our y equals. So I'm going to press y equals, and alpha y equals pulls up the numerator over denominator feature. If you don't have that on your calculator, you can of course type 1 divided by 79 and put that in parentheses. But since I have it, I'm going to use it. And the equation 768 plus 23x minus x squared. So the variable in our expression is a t, but it doesn't matter. Our calculator will interpret it the same as if we're using an x, as long as these variables match. So we have our function, and it's in our y equals. So now we just need to evaluate this expression. So 1/24, and if you press math option 9 is our function integration command, 0 to 24, and then alpha f4 will pull up the y1 variable. If it doesn't on your calculator, you can also access it by pressing vars, scroll right to yvars, function, and then y1. And that'll pull up the y1 there. And we're going to integrate with respect to x because the equation we put into our y1 was an x variable. And this gives us approximately 10.784. The AP test will take 10.785 as well. And then the unit on that is we're finding the average function value of the flow, which was in gallons per hour. So now if you have an old school calculator that doesn't have the integral command like that, I'll write down what you'd be typing. Function integration y sub 1 with respect to x on the boundary 0 to 24. Now they don't accept this as demonstration of work. They want to see the math notation up there. So this is just what you type on the calculator. All right, now let's look at where the points come from. So going back to part A is worth 3 points. So you're going to get your first point from finding the values r of 3, r of 9, r of 15, and r of 21. That's demonstrating that you have an understanding of what it means to do a midpoint Riemann sum. Then your second point comes from arriving at the correct numeric answer of 258.6. And then your third point comes from interpreting the meaning of your answer. Okay. So 3 points in part A. When we go on to part B, then there's 2 points on part B. The first point comes from saying that there does in fact exist a value C that this is true. So yes, there does. And then your second point comes from an explanation. And for me, all of the work here is demonstration of the explanation. I used mean value theorem. I could have done it with, I used Rolle's theorem. I could have done it with the mean value theorem, which is very, very similar. I'll put that in red. R prime of C equals R of 24 minus R of 0 over 24 minus 0. So it's just saying there exists a spot where the instantaneous slope equals the average slope. And for the case of the problem here, the average slope was 0. So Rolle's theorem or mean value theorem. And then finally, part C, also worth 3 points. This first point comes from, did you have the constant multiplier and the boundaries of 0 to 24? That's your first point. Your second point comes from, did you have the integrand? So did you know what function you were taking the average value of? And then your third point comes from, did you have the correct numeric answer? Now, if you'll notice, that only adds up to a total of 8 points. The ninth and final point comes from having the correct units. So the correct units, you have to have the units correct in part C as well as in part A. That's where your ninth and final point comes from.